The following content has been provided by RWTH Aachen University.
STNs are great, though, because, and you know this because you're computer scientists, so we've used automata to do other things with them, right? You can do all kinds of things with them. You can check, for example, for completeness. Can I get from any state to any other state? Which would be pretty useful if it's a user interface, right? You don't want to get stuck in one particular state in your user interface and not be able to get out of it anymore. You can also ask yourself, how easily can I get from one state to another one? And that will give you a measurement for how fast it is to operate the user interface to move between states. And it's something we can determine using basically algebraic principles and analyzing graphs. We can also check how hard is it to get back to a state that we just left. Let's say you accidentally pressed a button in the UI. How long does it take me to get back to where I just was? This is not undo, by the way, right? Because going back will mean that I will have changed something, but I'm back in the menu state where I was before. For example, I opened a drawing tool, and I want to get rid of it. Do I need to first draw a line, or can I just escape out of it? We can also look for dangerous states. Maybe there are states that the user normally shouldn't be able to go to, or that we want to avoid happening at all. And we can see how easy those are to reach, or when they happen. Let me give you an example for each of those. Checking transition properties like completeness. So for example, I know when I'm in circle 1 or in circle 2, I know what happens when I do a click. I click, and that basically draws the circle. In line 2, in this state, I know what happens when I click. I do another line segment. When I double click, I complete the polyline. I don't know what happens when I double click here. I didn't specify that. So that means the STN does not have a transition for what happens with the double click in this state. What do you think should be the default semantics of something that is not specified in an STN? What should the system do when a user input happens that isn't specified?
Ignore.
Ignore, yeah. That would be the default implementation, right? So by default, this would mean, since we didn't specify what a double click should do, the system would do nothing, right? Because this was not a valid input, if you like, not a valid transition to move out of that state. But maybe, as a designer, you now come in and say, as a usability expert, you say, wait, if the user double clicks on a circumference, surely they want to just complete the circle and just accidentally double click instead of single click. So let's make that an option here to double click and lead to the same state. Or maybe something else is supposed to happen. So that's where your design decisions go in and get immediately documented in this thing. So that sort of discrepancy here, having double click once and not having it in a different part, is being resolved. Here's another example. Reversibility. How easy is it if I accidentally selected the line menu in the graphics submenu to get back, to just get out of the line, out of this whole thing here? Well, we can see once I entered the graphics menu and picked sort of the line tool, I need to actually, because there's no other way to get out of this, at least not according to the STN, I need to actually go ahead and first click on this thing, then basically double click to get to the last line, and then I need to basically go all the way back to the main menu, and then I need to select the graphics menu again to actually get back to the same state. So that's a lot of work, right? That's a lot of work. And we might want to look into, can we make this easier? For example, offer a universal escape, where when I press escape key on the keyboard, I just basically exit out of the current submenu. Important, again, we're not talking about undo here, right? I'm talking about even if I, for example, accidentally started burning a CD in a CD burning software, how do I get back to the state that I was in before? Of course, I've started burning the CD. I can't undo that, right? But how can I cancel at least the burning state and get back to the state where I can maybe exchange the CD and put another one in because I don't like the one that I was starting to burn right now. Finally, dangerous states. Here's an example of that. This is a word processor. Imagine a word processor, like you're typing text, and it has two different modes. It has one mode in which you basically edit your document, and then it has a different mode where you basically do commands. And this is not that unusual. For example, the VI editor actually works in that kind of way. So this editor, this particular editor design that we're looking at here, uses the F1 function key to change the mode. So you move between the edit and the menu mode with F1. So you press F1, you edit your text, you do all kinds of deletions, insertions, and so on. You press F1 again, you're back in the menu state. From the menu state out, and only from there, you can press F2 to exit the program. And that will actually save the data. So great. If you press escape here, nothing happens. You stay in that menu, in that mode. The only thing is, when you do press escape, that's a special command that you can do in the menu mode to reset the autosave counter. You know, when you edit a text, as soon as you start changing it, you usually get a little marker that says this file has been changed since it's last been saved, right? So then you would reset that with this escape key, saying like, ignore the fact that I've accidentally typed in this file. I want this to be considered unchanged. It doesn't remove your changes, but it turns off the autosave. It won't save it when you exit. Now, this can be a useful function to behave as if a file wasn't changed. But it does create a dangerous state, right? Because when you're editing your file, and you go to the menu state and you press escape, then you've basically told the system you can ignore the changes that I've made. You could now exit without saving. It'll be OK with me. That's a dangerous area to be in. So the escape key has a dangerous function here. If you then, after that, go back with F1 to editing, and you make any change to your file, you get back into the safe zone because the autosave marker is turned on again. So we're good, right? If we then press the menu F1 and F2 to go to the menu key and go to the main menu and exit, it would save. The only thing that's a dangerous path here is if we were to press F1 to get from edit to menu, then press escape to say ignore the changes, don't consider this file unchanged, and then press F2 because then F2 would exit the application without saving our file. And that's a dangerous situation. You might want that sometimes, but it's a dangerous state to be in. But they're protected by the escape key, right? Pressing the escape key is the only way to get into the danger zone here, and any update in your file will get you back out of it. And this design was perfectly fine with the old keyboard layout that this was made for. Back in the days, they had keyboards where the function keys were to the left of your main keyboard, maybe in reminiscence to the design of the Alto and Star that had these special keys there. So you can see the escape key is nicely distanced from the F1 key. So a typical operation would be edit, 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 edit. You type your diploma thesis, your master's thesis, you're done. You hit F1, F2. The system goes into the menu state, goes exit, saves your file, everything's great. You do that every day, right? F1, F2, done for the evening. And if you ever need the special function, you'd hit the escape key up there, and that's a very special thing, so you don't do it accidentally. Problem is, if you look at your laptop keyboard, any modern keyboard looks like this. So you can now see what can happen, right? So you press F1. You want to hit F1, F2 to go to the menu and save and exit, but your finger catches the escape key, so you press F1, escape F2, and within a single gesture, you've destroyed your whole bachelor's thesis. Not a good idea. So what we can see from this is we can actually visualize with a state transition network the problem that we're running into here. We can analyze the problem and communicate it to other people thanks to the STN. So the state visualization and the real-world situation of where the keys are placed on the keyboard together give you a good picture of this possibly dangerous interaction. There are more things you can do. You can determine, for example, are there several arcs leading out of one state that have the same action associated with them? That means the system is non-deterministic. Maybe you want that. Maybe you want the system to take different paths based on what you do. If it's deliberate, then the application should have some algorithm to decide which one to pick. If it should really be truly random, then you would model it using production rules. You could model things like nested escapes. So when you hit escape to get out of a submenu and further out of that one, you can check for consistency. I have actions on my different transitions, right? Every arc has an action. For example, I could check across my whole STN, whenever I press escape as an action, does that lead to a follow-up state that is somewhat related? Is it always the same kind of action? We can even see things like modes inside state machines, so we can determine whether the same action based on where I was before has some totally different outcome. That's basically the definition of a mode, right? So these things are great, and we will talk about more about this in current topics in HCI next semester. So it's also an awesome class to come to. And we'll tell you more things about how you can use STNs to formally and mathematically determine qualities of user interfaces. Now I want you guys to try something before we head out here. This is going to be a little pre-lunch brain teaser. And I know you're low on calories right now, but I think you can do it. So despite your blood sugar level, here's the question. Imagine you have to have this simple dialogue. Just a dialogue that has how many different states? Hmm?
8.
8. I heard 8. Somebody said 8. So bold on off, italics on off, underline on off. Those are the 8 different states that this dialog can have, right? Let's assume you want to model this simple dialog, and you want to model it using a state diagram. So you'll need a little bit of a piece of paper here for this exercise. We can do this. This is 10 more minutes. I'm sure you can manage. First thing we do is just grab a piece of paper and with your neighbor draw a very simple dialog, just the bold option. Imagine a very simple dialog that has only the bold option available. What does the state transition network look like? Just for bold. This should be easy enough, right? We basically just have a regular style, and when you click the bold button, the bold checkbox, sorry, you move to the bold state. When you click the bold checkbox again, you move back to the regular style. Easy enough. So once we understood how the bold button works, how can you extend this to also include italics? Right. This is not quite so obvious as the last one. You basically, as you were saying, you have to basically extend each state with a mirror state. One thing is important to understand here. There is no single bold state anymore. Each state describes one state of this dialog, and the dialog now has 2 boxes. So a state always have to tell me what's the bold setting and what's the italic setting, right? So that's why the regular style means bold is off and italics is off. That's one state. The next state is bold is off, italics is on. That's down here now. Then there is italics stays off, but bold is on. That's what I get by clicking on bold. So then I have bold only. And then finally there's a state where both of them are on, bold and italics. That's by clicking on bold and then italics, or by clicking on italics and then bold. You can't get directly from the regular one to this one, because that would mean 2 interactions at once. OK? Should be fairly clear. And now add underline to this. So what does that look like? So with adding this other option, how many states do we have then? 8, right? So we realize a pattern here. We have to duplicate this entire automaton, put it next to this, and then connect over, right? So we now have this. We have the old existing one in the back, if you like, and we have the new one that's in front of it here, those 4. And it's the exact same automaton, but all the ones in the back have basically underline off. All the ones in the front, the 4 here, have underline on. And you get to any one in the back, to the one in the front, by simply clicking or toggling underline. Right? You probably have something similar, maybe not in this like fancy cube layout, but that's the general idea. You're doubling the entire state transition network, and the transitions to the mirror version are just the toggles in that new options. That's because all of these things can be on and off independent of each other. And now let's say you want to add, I don't know, capitals as a 4th version. And I love that option because I get to say hypercube in a lecture. So we now have a hypercube, which is a bit hard to draw in 2D or even 3D, but you can imagine it like this, right? It's basically one cube with these 8 options. It's the mirror image of that same cube, again with the 8 options. And what's leading from one to the other is then always the capitalized on-off toggle, the blue ones that we've added here. So that's what we call state explosion. In general, when you combine 2 of these STNs, you get to a new STN that basically has the factor, the result of the multiplication of the number of the states of the two machines. This makes it very hard to see the clear structure of the dialog, right? This complex hypercube thing doesn't look like a simple dialog with 4 checkboxes, right? This has to be something easier. And we will get to an easier description in the next class. This is especially a problem with modern GUIs because they allow you to do a lot of things in parallel. So all of these different state changes are possible in parallel, so your state transition networks tend to explode. There's a similar problem when you have an escape or help option. For example, when you have an escape to get out of a dialog without applying the changes, or a help button that can be used wherever you are, it really gets messy. Because let's take the example of the escape button. If I'm anywhere in this graphics submenu here, I want to be able to press the escape button and basically get out of the submenu back to the main menu without applying the changes that I did. You can make up a helper notation like this, like with these, this is the normal exit, but this basically means anywhere in this submenu, escape can be used. I would have to go there from every single node and make a line via escape to the main menu to have a complete state transition network. That gets messy, and so you will start coming up with shorthands for that. Even worse if you have help. Because let's say I bring up a help page, and let's say it even actually contains the exact same stuff. It doesn't need to be specific to the state. But the point is, when I'm done with the help, and I want to close the help menu, I need to go back to where I was before. So I need to hold on to where I was before I invoke the help menu. That means if I click help in the circle menu, then I end up in the help subsystem. But when I leave that again, I need to go back to the circle. When I'm in this other circle 2 state, I've already clicked on the center rubber band, and now press the help button. I need to open the same help subsystem, but somehow I need to remember that I now need to go back to circle 2. And in the state transition network, that means I need to hang this little help thing off every single state. So that also gets very messy, and usually we'll be using some kind of shorthand notation or make a note saying, help always goes back to the state where I was, and I'm not going to add that to the STN. But I think this shows the problems of STNs, and we'll see another way of doing this that's a more elegant way to deal with concurrency in next week's class. Thank you very much for listening, and I'll see you again next week.
This content was provided by RWTH Aachen University.